Dear students, this is solid state lecture number 3. In today's lecture, we are going to discuss about the different types of lattices, and then we will discuss all about the lattice types in 2 dimension and 3 dimension briefly, and then I will show you some of the pictures of the lattices, particularly Brevis lattice in 2 dimensions and 3 dimensions as well. So now let's start. Types of lattices in 2D are 5, and in 3D lattice types are 14. And what the basic question is, what are Brevis lattices and what are non-Brevis lattices? Basically, there are 2 types. So, Brevis lattices are those lattices which are consistent with point group symmetry operations. But the question is now, what are the point group symmetry operations? In previous lecture, we discussed 4 types of symmetry operations. Number 1, translation, then reflection, then rotation, and inversion. In these 4 operations, the 3 operations, number 1, rotation, reflection, and inversion. Combination of 3 such operations form some group of operations. Like in previous lecture, I show you 10 type of point operations like 1, 4, 3, mm, like this. Okay, if अगर आपको आवाज सही तरीके से clear नहीं आ रही, then don't worry, there may be network problem. I will upload the lecture on YouTube as well. But on my side, the internet is going very fast, so I think there should not be the problem of audio. If still there's an audio problem, then don't worry and go to the YouTube after the lecture. I will upload it in just 10 to 15 minutes after the lecture. Okay, so 4 type of operations we studied in the previous lecture: translation, rotation, reflection, and inversion. And 3 of these 4 types, excluding translation, these 3 operations form some group of operations which is called point group symmetry. Why we call it point group symmetry? This is due to the fact that these operations are centered on a single point. For example, this is a single point and we take a rotation. So rotation is along a single point. We are not moving in the space. If there is a reflection, and if this is a let's suppose image, and then it has a reflection on the back side. And similarly, inversion, then if we have moved towards positive R and move towards the negative R at the same distance, and the system repeats its symmetry, it will have the inversion symmetry. So all of these symmetry forms a group called the point group symmetry. And there is a space group. What is a space group? Space group is if we add translation in all these combinations, reflection, rotation, and inversion includes translation from one point to another point, and that is known as space group. Space group is actually a combination of all 4 types of symmetry operations, but point group is a combination of 3 types excluding translation. So these are simple definition of space group and point groups. There are a total 10 point groups in 2 dimensions, and there are 32 point groups in 3 dimensions. So the lattices which are consistent with point group symmetry are known as Brevis lattices. But those lattices which are not consistent with the point group symmetry are called non-Brevis lattices. What it means, how something is consistent with the point group symmetry. It means that if we form an operation on a Brevis lattice, it will give you this identical position of the lattice. So it means it is consistent with the point group. And if the shape of the lattice is totally changes, and we can notice that change, then that is not consistent with the symmetry operation. So those lattices which are consistent with the symmetry operations are known as Brevis lattices. So in 2 dimension, there are 5 types of the Brevis lattices. I'll show you on the share screen. So let me show you. Okay. These are the Brevis lattices on the screen. There are 5 types of the Brevis lattices. I will explain one by one each one. In the A figure, it is called oblique Brevis lattice. In 2 dimension, I'm talking. So there are 2 sides. One is the A side, other is the B side, and other 2 sides are actually the reflection of these sides. And in oblique geometry, A and B are not equal. It means 2 sides of the lattice are not equal. A and B are the crystal axis we have already defined. And these 2 crystal axes or translation vectors or crystal axes are not equal. Length of the 2 vectors is not equal. A length is not equal to B length in oblique. And angle between the 2 lines, this is called gamma angle. Gamma angle is not equal to 90 degrees. So in oblique geometry, there are two specifications, that both of the sides are not equal and the angle is not equal to 90 degree. This is called oblique Brevis lattice. Why we call it Brevis lattice? Because it is consistent with the point group symmetry. It's not violating the point group symmetry. If you make some symmetry operations using the combination of reflection, rotation, and inversion, it will give the same value, same position, same picture, same drawing, you can say. And the second is the rectangular primitive. Actually, this is the crystal type rectangular, but rectangular have further 2 categories. One is the rectangular primitive and the other one is rectangular centered. Rectangular primitive, as you know from the definition of a rectangle from the basic geometry, that both sides are not equal of a rectangle. In a sphere, both sides are equal. So in a rectangle, A length is not equal to B length. B length is shorter than A. And the angle between that vector A and B is exactly equal to 90 degrees, unlike oblique. In oblique, sides are not equal and angle is also not equal to 90. But in case of rectangular, both sides are equal and the angle between the 2 sides is 90 degrees. And this is actually rectangular primitive. In primitive, all the lattice points are at the corners. कॉर्नर्स के ऊपर सारे पॉइंट्स पाए जा रहे हैं, कोई भी पॉइंट इसके मिडल में नहीं है, तो इसको हम क्या कहते हैं? We call it rectangular primitive. And the other type is rectangular centered. Rectangular centered, again both sides are equal and the angle is 90 degree. But the difference between the primitive and centered is that there is a point in the center of this geometry. This is the basic difference. There is no point in the primitive at the center, but in a rectangular there is a point at the center as well. Corners पर भी points हैं और center के ऊपर भी point है, जबकि rectangular में क्या है कि just corners के ऊपर points हैं, center के ऊपर कोई point नहीं है. तो रेक्टेंगुलर सेंटर्ड और रेक्टेंगुलर प्रिमिटिव में एंगल्स भी इक्वल हैं, साइड्स भी इक्वल हैं. रेक्टेंगुलर प्रिमिटिव में जस्ट कॉर्नर्स के ऊपर हैं इसके पॉइंट्स, और रेक्टेंगुलर सेंटर्ड में इसके सेंटर पर भी पॉइंट है. जिस तरीके से प्रिमिटिव की डेफिनेशन भी आपने पढ़ी थी प्रीवियस लेक्चर्स में कि इसमें इफेक्टिव नंबर ऑफ पॉइंट्स क्या होंगे, 1 होंगे, 1/4 इसकी वजह से कंट्रीब्यूशन होगी, तो 1/4 इस वजह से, और 1/4 इससे, और 1/4 इससे. तो टोटल जो आपके पास नंबर ऑफ इफेक्टिव पॉइंट्स हैं प्रिमिटिव में वो 1 होंगे, जबकि जो रेक्टेंगुलर सेंटर्ड होंगे उसमें ग्रेटर देन 1 हो सकते हैं. दिस इज नॉन प्रिमिटिव एक्चुअली, and we call it centered because 1/4 plus 1/4 plus 1/4 plus 1/4 equal to 1, and plus this one, this is actually total number of effective points are 2 in the rectangular center. And then after that we have another type of the Bravais lattice in 2 dimension, that is a square. In square both sides are also equal. In rectangular both sides are not equal. Okay, in rectangular both sides are not equal, but in case of square both sides are equal, and the angle between the side is also 90 degree. So you can check that this side A, this side B are both equal in length, and the angle is also 90 degree. So this is the square symmetry. And the last one, last Bravais lattice type is hexagonal. In hexagonal, sides are equal. A side is equal to B side, but the angle is not equal to 90 degree, angle is 120 degree. So this is a brief description of the Bravais lattice types in the 2 dimension. There are actually 4 types of crystal systems. One is oblique, one is rectangular, one is square, one is hexagonal. 4 types of crystal types, but 5 types of Bravais lattice. Why 5? Because rectangular crystal type have further 2 categories. One is a rectangular primitive, one is rectangular centered, but all other oblique, square, hexagonal, and the other one have the one type. So 5 type of total Bravais lattices in 2 dimension. Okay, all right, now let's move toward the types of lattices in 3 dimension. Actually there are 7 crystal systems in the 3-dimensional system, but 14 Bravais lattice types. 7 crystal systems in 3 dimension and 14 Bravais lattices, because each crystal system have further categories. I will show you the 7 crystal systems now in a picture. Okay, the first crystal system is cubic. In 3 dimension I am talking. Cube is not a 2-dimensional symmetry. It always requires 3 dimensions. So it is categorized in a 3-dimensional crystal systems, and we are now going to define 3-dimensional crystal systems as well as Bravais lattices in 3 dimension. Okay, let's move quickly towards the 3 dimension. Okay, number 1 is cubic. Cubic system, crystal system have all sides A, B, and C equal. Now notice that in 2 dimension we have defined 2 sides A and B, because we were talking in the 2 dimension. Now we are going to talk about 3 dimensions, so we will define 3 sides. Okay, so 3 sides and 3 angles as well. So in cubic system all 3 sides are equal. You know well from the definition of a cube that all sides of a cube are always equal, and angles alpha equal to beta equal to gamma equal to 90. All angles are 90 degree in a cube, and all sides are equal to each other. That is the definition of a cubic system. This is the most symmetrical system, crystal system in 3 dimension. Then tetragonal. Tetragonal have two sides equal. A is equal to B, but not equal to C. Third length is not equal. And all angles are equal. Alpha, beta, and gamma are equal to 90 degree. All angles are 90 degree in tetragonal as well. In orthorhombic, all sides are not equal. A is not equal to B, is not equal to C. All the lengths are not equal to each other, but all angles are still 90 degree. And in rhombohedral, all lengths are equal, but all angles are not equal to 90 degree. They may be differ. They may differ from the 90 degree. And hexagonal, in hexagonal crystal system, two lengths A and B are equal, but the third length is unequal, and angles are again equal to 90 degree. In monoclinic, all sides are not equal, and two angles alpha and gamma are equal to 90 degree, but the third angle beta is not equal to 90. And triclinic systems, all lengths are not equal to each other, and all angles are not equal to 90 degrees. So this is the less symmetrical, least symmetrical from all these systems. Cubic is the most symmetrical, and on the other end, triclinic is the least symmetrical system. So these are 7 crystal systems in 3 dimensions. But there are 14 types of Bravais lattices in 3 dimension, because every crystal system have further specifications. For example, if I show you from the picture, let me check it where it is. Okay, right. Okay, for example, cubic system. Cubic system have further 3 categories: simple cubic, face centered, and body centered. I try to show you what is the difference between simple cubic, body centered cubic, and face centered cubic. Now, cubic system have 3 types of further categories in the Bravais lattice. One is a simple cubic. Simple cubic means there are only crystal points at the corners. Only at the corner. This is the simple cubic geometry. Only at the corners it has the lattice points in space lattice. So again, angles all sides are equal, and all angles are 90 degrees, just like in general in cubic, but the lattice points are only at the corners of the each cube. So such type of cubic Bravais lattice is called simple cubic. Next comes body-centered cubic. Body-centered cubic means there are lattice points at the corners, and there is a single point in the middle at the center of the cube. That is why it is called body-centered. Body-centered means that there is a point, there is a lattice point at the center of the box. Center of the box पे आपके पास पॉइंट है, जिसकी वजह से हम इसको क्या कहते हैं, हम इसको बॉडी सेंटर्ड कहते हैं. And there is another type, face centered cubic. Face centered cubic means a cubic Bravais lattice which have lattice points at the corners, but there are also lattice points at the center of each face. You know, cube has 6 faces: front, back, right, left, up, down. So there is, you can see from the screen that there are points at bottom. There is a point at the center of the left side. There is a point at the center of the right side. There is a point at the center of front side. Top side, there is a point at the center of the front side. There is a point at the center of back side. So all 6 faces of the cube have a lattice point. So this is called face centered. Again, I repeat, in simple cubic, there are only points at the corners of the cube. So that is called simple cubic. and there are body-centered cubic. Body-centered cubic means in spite of the points at the corners, there is also a point at the center of the body of this cube. That is why it is called body-centered cubic. And there are face-centered cubic. Every face, every side of the box contains a point, a lattice point. At the front, at the back, at the right, left, top, bottom, every side at the points. So three types cubic system have further. So there are three Brevis lattices in the cubic crystal system. There are two further systems in the tetragonal, which have simple and body center. Body center again means there is a point at the center. And further, the next crystal system is orthorhombic. Orthorhombic have simple orthorhombic, body centered, orthorhombic, end centered, and face centered. End centered mean top and bottom. There are points, lattice points at the top and bottom only, not all the faces, but at the top and bottom we call it end center, because this is the top end, this is the lower end. It contains a point, so we call it end center. And similarly, rhombohedral have further two, simple and simple hexagonal. Simple hexagonal have angle gamma equal to 120 degrees in particular. And then we have a monoclinic system, simple and end-centered, and triclinic and at the end. So you can count these are the 14 types of Brevis lattices in 3 dimension. But now there is a question. Question is that end center is only present in, for example, orthorhombic, but why not it is present in the simple cubic, in a cubic system? Why is not end center is not present in cubic? While you can say another question that suppose why rhombohedral have no body centered rhombohedral? The answer is that in some systems, when we draw a body-centered structure, it will give the other existing structure. So we do not have to draw that structure. For example, in cubic, if we draw an end-centered system, that has another way present in the orthorhombic. So we do not need to consider that point. So the scientists have checked all the symmetries and all operations. At the end, they concluded that the Brevis lattice has only 14 types in, you can say, 3 dimension. At the end, I will discuss again effective number of points. How to calculate effective number of points? We have already discussed in the previous some lectures, but I will tell you a formula to again to memorize how to calculate the effective number of points. I try to show you. Okay, this is the formula. N is equal to Ni plus Nf by 2 plus Nc by 8. N is the total number of effective points. Ni is that number of points which are at the center. I represent the central index. Nf is the number of points at the face divided by 2. Why divided by 2? Because each face is divided by 2 you can say unit cells. If this is a you can say one box and this is the other box, then the middle line shares from this side as well as from this unit cell. So face centered point is always divided by 2, and in 3 dimension the corner point is divided by 8 unit cell. If you draw a cube, then there at each corner of the you can say box, there are 8 boxes, one at the top, one right, one left, and down, and from every sides 8 cubes share a corner point. So that is why NC is divided by 8. So total number of effective points can be calculated in a three-dimensional system equal to Ni, which has the full contribution at the center, because at center no other unit cell divides the that point. At the face, there are two sides. If I may show in this picture, if let's say there is a point, it will be divided from this unit cell as well as from this unit cell. And at the corner, at this point, there are 8 positions in 3 dimension which divide this point. So face point is divided by 2 and corner point is divided by 3. So this is today in today's lecture. I just going to summarize the ideas. I have discussed the types of Brevis lattices, point groups, space groups, and how to calculate number of effective points. So point groups are the reflection, rotation, and inversions, and their combinations. Different symmetry groups are called containing the reflection, rotation, and inversion are called point groups because they operate on a single point. And if we include translation in with the all other 3 operations, that is called a space group. And those type of lattices which are consistent with the point group symmetry operations are called Brevis lattice, which have 5 types in 2 dimensions as I have discussed with you, and 14 type of Brevis lattice in 3 dimension. And those lattices which do not synchronize with the point group symmetry operation, which are not consistent with the point group symmetry operations, are called non-Brevis lattices. That's all. If you have a question, you may write in the chat box, or you may send me an audio message in the WhatsApp group. Okay, anyone?